Hi, welcome back to our last example in 1.3, a maximum or minimum of a quadratic function. In this example, we will be connecting projectiles to quadratic functions, and we will solve for the missing information using technology. Jamie throws a ball that will travel through the air with a parabolic path due to gravity. The height h in meters of the ball above the ground after t seconds can be modeled by the function h of t equal to negative 4.9 times t squared plus 40t plus 1.5. We can see that is a nice equation for a quadratic. I can also see the leading coefficient is negative 9, so I know this opens down. I also can see the y-intercept, 1.5. So I do have a little bit of information about this already. So it says find the zeros of the function and interpret their meaning. So when they're asking for the zeros, they're asking for the x-intercepts, right, on the graph. So using technology, this kind of becomes quite easy. So you can enter in the equation into your graphing calculator and make sure that you enter it in like this. That way you can get the equation of a quadratic. Okay, and I'm going to just use Desmos for simplicity, and I'll be entering that same equation in here. So we have y equal to negative 4.9 times x squared. By the way, also, just to point out, if you're using Desmos, when you enter in negative 4.9, you want to use the negative symbol and not the minus sign on your graphing calculator. Okay, there is a button that's used for subtraction, and there's a button that's used to show something's negative. So you want to make sure you use the negative symbol. Okay, I can go over on that, go over that in class with you guys if you need to. All right, so back to this. I'm just going to add the rest of this equation: 40x plus 1.5. Okay. All right, I kind of got all the information in here. It's really nice when you have graphing technology. I can get the maximum point. I can get one of the x-intercepts. I'm going to zoom in. Notice here it's a little bit tricky, but there's our y-intercept, the 1.5, which I pointed out earlier. And our other x-intercept is at negative 0.0373. So obviously for this question, we're looking at a height function. Okay, so the height depends on time, right? We're obviously only want to look at like positive time. Um, if we were stating domain and range for application style question, we want to limit time to just positive values. So, but in these questions, they're just asking for information on the graph, so we're going to give them that information. It says find the zeros of the function. So we have the first zero there. So solution, part A. I'm just going to draw a little picture of the graph. I'm kind of going to exaggerate things a bit. So this one was at negative 0.037, and the next one was at 8.2. I guess I could do the 3 decimals. Yeah, that would be fine. Okay, those are the two values for that. This is height versus time. So those are my answers. Those are the two zeros. Okay, it also says interpret their meaning. So this makes sense. At t equal to 8.201 seconds, the ball lands on the ground. Okay, that means the height would be 0 at that point. Okay, now this one doesn't really make too much sense, right? The negative 0.037. It's also saying like the ball was thrown at time negative 0.037. Well, it doesn't really make sense. So the ball must have been thrown at time 0. Okay, we can't go back in time and then throw the ball. So it doesn't really make sense. But this is more just showing, um, like we know the ball would have been thrown from the height of 1.5, the y-intercept. So if we could, the negative time just means if you were to go backwards, trace backwards along the graph, that would actually be when it was at a height of 0. So we could say here for this time, the solution, or we could say, yeah, we'll say the solution or the 0, t equal to negative 0.037, indicates when, and we'll say in the past, the ball would have been thrown. From ground level. Okay, so if the ball was thrown from ground level, it would have had to go back in time like 0.037 seconds. So that's all. Okay, part B. So that was part A. Now part B. Determine the time needed for the ball to reach maximum height. So we can get that straight from the graph. I'm looking at the x value, 4.082. So 4.082, comma, 83.133. Okay, so this x coordinate, it's actually a time coordinate. That one's written first. So we can see at time 4.082 seconds, the ball's at the maximum height. Okay, what we could also do is another way, if we couldn't really get this point on a graph, we could calculate the axis of symmetry because we know that's where the maximum occurs. So we could just find the average of these two values. And notice 4.082 looks like the average between those two numbers. Okay, and last question C, what is the maximum height of the ball? Well, we have that right here on the as our order pair. So we could say 83.133 meters is max height of the ball. Okay, we could also take this time when max height occurs and we could go up to our graph and we could plug it in for x and actually calculate the y value, the height value. So that would be an alternative approach. Hope you found this helpful, and we'll see you next time.